Swayam Prabha. Digital India. Educated India.
Welcome to the class. Today we are going to see the examples on steam turbines. One example reads that the velocity of steam entering a simple impulse steam turbine is 1000 meter per second and nozzle angle is 20 degree. The mean peripheral velocity of the blades is 400 meter per second and the blades are symmetrical. If the steam enters blades without shock, find the blade angles. A. Neglecting the frictional effects on the blades, calculate tangential force on the blades and diagram power for a mass flow of 0.75 kg per second. Estimate also the axial thrust and the diagram efficiency. If relative velocity at the exit is reduced by friction to 80% of its inlet value, estimate the axial thrust, diagram power and diagram efficiency. So, we will first plot the velocity triangle and then we will note whatever it is given to us. So, let us say that this is VB, this is V1, so this is VR1 and then this is VR2. And this is V2. So, what we have is this is alpha, this is beta 1, this is beta 2. Okay. So, noting this, we can proceed. For A, we are said that we have to neglect the friction factor. So, Kb is equal to 0. We have been told that the turbine is impulse turbine. Okay. So, since the turbine is impulse, we have degree of reaction equal to 0. So, VR1 is equal to VR2 since we have Kb also equal to 0. Further, we are also told that blades are symmetrical, so beta 2 is equal to beta 1. So, with this point we can start, then we will note that directly VR1 sin beta 1, which is basically VA1 parallelly VA2 is equal to VR2 sin beta 2, but what would happen, VR1 is equal to VR2, beta 1 is equal to beta 2, so VA1 is equal to VA2 is equal to VA, so we will have VA is equal to VR1 sin beta 1 is equal to V1 sin alpha. So, this height. So, for this we can just equate this much part and then we can have one more thing, that VR1 cos beta 1 plus VB. So, this is VB and this is VR1 cos beta 1 and this is VB. So, this is total is plus. So, for this plus we have equal to V1 cos alpha. So, we have VR1 cos beta 1 is equal to V1 cos alpha 1 basically V1 cos alpha minus Vb. We can divide these two equations, this and this, and then we have tan of beta 1 is equal to V1 sin alpha divided by V1 cos alpha minus Vb. So beta 1 is equal to tan inverse V1 sin alpha divided by V1 cos alpha minus Vb. So now we have beta is equal to tan inverse V1 is given to us, which is 1000 meter per second. Nozzle angle is told to us as 20 degree divided by V1 is 1000 into cos of 20 minus Vb is given as 400. So this beta turns out to be 32.35 degree, and since blades are symmetrical, beta 2 is equal to beta 1 is equal to 32.35 degree. So we found out the angle. Now we can move ahead and then we can find out VR1 is equal to, we know VR1 is equal to VR1 sin of beta 1 is equal to V1 sin alpha. So we know VR1 into sin of 32.35 is equal to V1 1000 into sin of 20. So we have VR1 is equal to 639.25, and this we know since we have no friction, VR1 is equal to VR2, and both are 639.25 meters per second. So now we know VR1, VR2, beta 1, beta 2, and then we can now calculate the desired thing. So for that we can go ahead and calculate delta VW, which is VR1 cos of beta 1 plus VR2 cos of beta 2, but we know VR1 is equal to VR2, cos beta 1 is equal to cos beta 2, so it is 2 into VR1 into cos beta 1. So we have delta VW is equal to 2 into 639.25 into cos of 32.35. So we have delta VW is equal to 1080.07 meters per second. So we can find out thrust or force, which is equal to change in momentum. So it is equal to m dot into delta VW, and now we are given that m dot is 0.75 into change in velocity is 1080.07. So thrust or force is equal to 810.05 Newton. So this is the tangential thrust. Now we can find out the axial thrust, which is equal to VR1 sin beta 1 minus VR2 sin of beta 2, but again VR1 is equal to VR2 and beta 1 is equal to beta 2, so this is equal to 0. So we have, this is basically axial change. Change in axial velocity which is delta VA. So axial thrust is equal to m dot into delta VA, and that is 0. So power, and since we are finding out that power from the diagram, so which is diagram power is equal to the force which is axial thrust into velocity which is VB. So power, diagram power P is equal to 810.05 into 400, that is equal to 324.02 kilowatt. So this is the power, diagram power. So we can find out diagram efficiency, which is equal to diagram power divided by half m dot into V1 square. So here we can put it as 324.02 into 10 to the power 3 divided by half into 0.75 into 1000 square. So we have diagram efficiency is equal to 0.864. Now we can move ahead for the second part of the same example, where we are told that friction factor is 0.8. So we are told that VR2 upon VR1 is equal to 0.8. So we have VR2 is equal to VR1 into 0.8. Our calculation of beta, our calculation of VR1 is intact. It will be same as what we did for part A. So we will carry forward with the same VR1, which is basically 639.25 into 0.8. So we have VR2 is equal to 511.4 meter per second. So we have delta VW, which is VR1 cos beta 1 plus VR2 cos beta 2, and now this will be 639.25 into cos of beta 1, which is 32.35 plus 511.4 into cos of 32.35. So we have delta VW is equal to 972.06 meters per second. So we have thrust is equal to m dot into delta VW, and then that is equal to 0.75 into 972.06, and this we can find out 729.05 Newton. So power is equal to thrust into VB. So it is 729.05 into VB is 400. So this gives us magnitude 291.62 kilowatt. Similarly, we can find out change in axial velocity is equal to VR1 sin beta 1 minus VR2 sin beta 2 is equal to delta V. So we have axial thrust is equal to axial thrust maybe TA is equal to m dot into VR1 into sin beta 1 minus VR2 into sin beta 2. We can find out TA using all numbers which are known to us. So we can put VR1 over here 639.25 into sine of 32.35 minus VR2 is equal to 511.4 into sine of 32.35. So axial thrust for us is 51.3 Newton. So this is how we can solve the example which is for the impulse turbine. We will move ahead with the next example, and it reads that an impulse steam turbine has a number of pressure stages, each having a row of nozzles and a single ring of blade. The nozzle angle in the first stage is 20 degree and the blade exit angle is 30 degree with reference to the plane of rotation. The mean blade speed is 130 meter per second and velocity of the steam leaving the nozzle is 330 meter per second. Taking the blade friction factor as 0.8 and nozzle efficiency as 0.85, determine the work done per stage per kg of steam and the stage efficiency. If steam supplied to the first stage is at 20 bar 250 degrees Celsius and the condenser pressure is 0.04 bar, estimate the number of stages required. Assume that the stage efficiency and the work done are same for all stages and that the reheat factor is 1.06. So we will start. So for that, let us draw again the velocity triangle. This is V1, this is VR1. This is VA1, beta 1 alpha, beta 2 delta. This is VR2, V2. Now we are given that alpha is equal to 20 degree. We are also told that beta 2 is equal to 30 degree. VB is equal to 130 meters per second and V1 is equal to 330 meter per second. So these are the things with us. Now we have also drawn the velocity triangle. So let us move ahead with part A. So here as well we can write down the expression as VR1 sin beta 1 is equal to V1 sin alpha, and then also we can know VR1 cos beta 1 plus VB is equal to V1 sin alpha V1 cos alpha. We can put the VB over here and then we can divide, and then what we got last time we will get the formula which is tan beta 1 is equal to V1 sin alpha divided by V1 cos alpha minus VB. So it is 330 into sine of alpha, alpha is 20 divided by 330 into cos of 20 minus VB is 130. And this gives us tan beta 1 as 0.627 and which gives us beta 1 is equal to 32.07 degree. So we can have VR1 is equal to, basically what we know VR1 from this equation we can write down VR1 is equal to V1 sin alpha divided by sine of beta 1. So we can write down it as 330 into sine of 20 divided by sine of 32.07, and then this gives us VR1 as 212.5 meters per second. So VR2 is equal to VR1 into friction factor is 0.8. So we have VR2 is equal to 170.25 meters per second. So we have got this all. So now we can know delta VW, which is VR1 cos beta 1 plus VR2 cos beta 2. So we have delta VW is equal to 212.5 into cos of beta 1 32.07 plus VR2 is equal to 170.25 into cos of 32.07, and this gives us delta VW beta 2 is given as 30 degree. So knowing this, we can find out delta VW, and this turns out to be 372.3 meters per second. We will go ahead and find out rest of the things. Till time we have found out delta VW. Blades are not symmetrical in this case, that's why we don't have betas are equal. We don't have betas as equal. So we have found out beta 1, beta 2 is already given. Now we have found out change in tangential velocities. So tangential thrust is equal to basically m dot into delta VW, and then power is equal to m dot VB into delta VW. So power is equal to m dot, let us assume 1 kg per second, VB is told as 130, and delta VW we have just find out 327.33, and then this power is 42.55 kilojoule per kg. So we can have diagram efficiency, and D is equal to power divided by half into m dot into V1 square. So we know it is 2, this 2 will go in the numerator, 2 into 42.55 divided by m dot is 1 into 330 into 330. So this is in kilowatt joule, so we can make it into joule. 330 into 330, and this gives us diagram efficiency as 78.15%. Now we can find out stage efficiency, and stage efficiency is nozzle efficiency into diagram efficiency or blade efficiency. So nozzle efficiency is 0.85 and diagram efficiency is 0.78. So we get it as 0.66. So this is the stage efficiency. Now we will go to the part B, and part B needs turbine efficiency in total, that is equal to nozzle efficiency, blade efficiency into reheat factor. So we have found out this as stage efficiency into reheat factor. So turbine efficiency or internal efficiency is 0.66 into 1.8 0.06, that is equal to 0.7041. We can find out enthalpy at the inlet to the nozzle from the given temperature and pressure condition, and that is equal to 202902.3. kilojoule per kg. Similarly, we will also note down entropy at the same location, which is 6.5466, and Sg corresponding to the same saturation pressure we can find out from the steam table, and then we can say that S2 is equal to S1 basically dash X SFG, and then from here we actually need S1 is equal to S2 dash. So we have basically S1 is equal to, this is SF plus X2 into SFG, and this gives us S, since S2 dash is known, and then we know SF, liquid saturation entropy for the condensation pressure, and then this is the latent entropy for the condensation pressure, and then we can know X from here, which is X dash is 0.7757. Knowing this, we can find out ideal enthalpy H2 dash at the exit of the nozzle, as so rest of the enthalpy is converted into kinetic energy. So this is available enthalpy with the flow. So this is equal to HF plus X2 into HFG, and then we can find out this as 2032.29 kilojoule per kg. So number of stages is equal to delta H total divided by delta H stage. So delta H total is equal to H2 minus H1 divided by delta H stage. Here H2 minus H1 is equal to turbine efficiency into H2 minus H2 dash. So H1 minus H2 dash. So we know this efficiency is 0.7041 into turbine efficiency is this into H1, and H1 is basically the enthalpy at the entry to the nozzle, and that is 2902.3. we are given that this is going to have a boiler at 20 bar and 250 degrees Celsius. So considering these two conditions, we can find out H1, this is the condition for 2 dash, this is the condition for 1. Knowing the state 1, we can find out H1, and we also found out H2. So it is minus 2032.29. So we have H2 minus H1 is equal to 612.57 kilojoule per kg. So this is the H2 minus H1 is equal to delta H total. So we have number of stages n is equal to delta H stage divided by delta H total. So delta H stage, delta H total divided by delta H stage, and delta H total is 612.57 and delta H stage is 42.55, and basically this is the power of diagram. So N is equal to 14.39, which is almost equal to 15. So we need 15 number of stages for this turbine. So here we have solved this example on impulse turbine.